there are special types of graphs or graphs with a special property that are called trees. And we'll talk a little bit later about some of the applications of trees and what makes this special type of graph useful. But for now, we want to get a sense of what a tree is. Now, the nice thing is that you're probably familiar with this idea already. It's a very intuitive concept to understand what a tree is in the context of graph theory. So here's an example of a couple of tree structures that you've seen before, or the kind of idea you've seen before. So the idea of a family tree, it's really a graph that does fit this category of tree. So trees are a subset of graphs. A special type of graph. So here's an example of a family tree, the Bernoulli family tree, which is a famous mathematical family. And the people here are not significant at the moment. Rather, we're just looking at the structure of this, how there's the sense of a tree branching out from a root in this case. Now, the definition of a tree may or may not seem intuitive at first, but it's a connected graph, that's important, and it has no simple circuits. So remember, a simple circuit is one where you can start at one point, take a path, and then come back to where you started without retracing your steps at all. So for instance, let's say I started here on this tree, and I tried to leave and then come back to this point without retracing my steps. It's impossible to do. No matter where I go, if I try to come back, I have to retrace my steps. I can't circle back around to that point. So that's all that the definition of a tree is. And that simple definition is enough to lead to this kind of structure where you've got branching out from kind of a central location. Here's another example of a tree that you've seen in different kind of ways before. If you look at the directory structure on a computer, you've got a tree structure where you have a root folder, and then under this root folder you have however many other folders you have, and then inside of those you have more, and so on. And so there's this directory structure that forms a tree, and each directory can be a parent directory or a child directory. You can build a tree like this. If you've done a fair amount of web programming or web design, you might have learned about what's called the DOM, the Document Object Model, which is basically how a browser keeps track of what's on the page that you're looking at. And so there are nodes on this page. These are nodes of a tree. And so there's child nodes and parent nodes and sibling nodes. And really it's a tree. It's all graph theory. So a lot of these ideas that we're going to talk about have a lot of applications in all sorts of fields, again, largely in computer science, but other fields as well. So that's what a tree looks like. And then we have some conditions here. And I won't have you worry too much about memorizing these or anything. These are mostly just different ways to think about recognizing a tree. Some are more helpful than others. So for instance, the first equivalent condition, in other words, this is another way of saying you can recognize a tree this way, if there's a unique simple path between any two vertices. So the idea of there being a simple path between any two of them tells you that it's connected, if there's a path between any two, and then the fact that it's simple and unique tells you that it's a tree, so you can't loop around back to where you were. The second one is a little bit more helpful to visualize whether something is a tree or not. So I use the term that it's connected but barely connected, meaning there's no superfluous edges. There's no edges you could take away that would leave it connected. So any edge you removed would disconnect it. And that can be kind of helpful when you look at recognizing whether a graph is a tree or not. The next one may be even easier. If the graph is connected, but there are one fewer edges than there are vertices, that's the same thing as saying either of the first two statements. So again, these aren't things to memorize necessarily, but as you look at homework questions, for instance, that ask you, is this graph a tree? You can use this sense. For me, the second one is maybe the most helpful visually. You can kind of think about, is there any edge here that I can remove that would leave it connected? And if there is, it's not a tree. But if any removal of an edge would break the connectivity, then it's a tree. The last one you can use because it's easy to just count things, so you can use that to check whether it's a tree or not. I have a couple examples here, and if you like, you can pause the video and see if you can identify which of these are trees and which are not, but then I'll give you the answers in a second. Let's look at the first one, for example. That one, first of all, is it connected? Yes, that one's connected. So there's any two vertices are connected by some path that you create. And then, is there any edge that you can remove that would leave it connected? And the answer is no. Any of those edges that you took away would leave one or more nodes isolated from the rest of the graph. So it's connected, but just barely, so it's a tree. You could also count and say there's 8 vertices and, 6 vertices and 5 edges, and so that fits the third category, the third description of a tree. For number 2, is it connected, first of all? It is, and you can see that easily visually, but there are some edges that are superfluous. So, for instance, if you remove the edge from A to D, you could still travel from A to D by going through B and E, for instance. So you could still get there. So there are some edges that you don't have to be connected. And you could also count, again, the vertices and the edges, and you'd find that there's not one fewer edge than vertices. So that one is not a tree. So the first one is a tree. The second one is not. The third one is a little tricky because it looks like a tree because there's no superfluous edges. There's no edges you could remove and still and break connectivity right away. But the fact that it's not connected to begin with means that it's not a tree. So if you're interested, this is what you call a forest, because it's a set of 2 segments, 2 pieces, each of which is a tree. So each of those pieces individually does form a tree, but since the whole thing is not connected, it is not one single tree together, but it is a forest. So some of this terminology is kind of intuitive. The language we use is maybe familiar. One more thing I want to show you here is the idea of a rooted tree. And both of the trees that I showed you earlier, you generally would think of as a rooted tree. So when we talk about a rooted tree, it's basically an extra distinction that we add on. We basically distinguish or designate one vertex as the root. So it doesn't change anything about the structure itself, it just changes how we think of it. So you can go to any tree like this. Say I looked at this example here, I could pick any one of these to be the root. I could pick B to be the root, or E to be the root, or whatever you want. So it's an extra piece of information that we add into the question, or we add into the discussion. We create this root idea. So it really depends on the application whether a rooted tree is helpful or not. You can think of with the directory structure we talked about, this is the language we use. We talk about the root structure, or the root directory, as being sort of the parent of all the others. And then we use language like you would use in a family tree, which is also a rooted tree. You can talk about siblings. So these 3 would be sibling nodes, because they're all descendants of the same, or they're all children of the same directory. So they all belong together. So you can talk about the child, which would be one step away from the root. So starting at the root, one step away from that would be its children. And then each one of those, if you take a step further away, you get their children. So you can go down the tree and up the tree. Down just means away from the root, and up means towards the root. And so you have this language, child, parent, and then you can have descendant or ancestor, which is more general. So child or parent is one step up or down, descendant or ancestor is arbitrarily many steps up or down. So the language is very familiar because it's the kind of language we use with a family tree, but any rooted tree you can use that same language for. So again, on a web page, when you have the DOM model that has a root node, which is usually the window itself, and then from that there are children, and those have children, and so on. And so you can traverse through this tree the same way you would traverse through the directory structure on your computer by going up and down through different folders. So trees, the general idea is relatively simple, and rooted trees just adds one extra piece of information by distinguishing or designating one vertex to be the root.